July 1940, and RAF pilots have a secret they won't admit to their commanders. They're more afraid of their own aircraft than the enemy. Hawker Hurricane squadrons are hemorrhaging pilots, but not from combat losses. They're burning alive. Defensive fire from German bombers hits the Hurricane's unprotected fuel tank, and burning petrol sprays directly into the cockpit through gaps in the instrument panel. Pilots have 8 seconds, maybe less, to bail out before the flames consume them. The statistics are horrifying. Between June and August 1940, 47 Hurricane pilots died from fire injuries. Not shot down, not killed in crashes, burned to death in aircraft that should have brought them home. Then came an unlikely solution from a chemical engineer who'd never designed an aircraft component in his life. Major John Wood proposed coating fuel tanks with a rubber compound that would automatically seal bullet holes. The RAF engineering establishment called it chemically impossible, said rubber couldn't withstand aviation fuel, said it would add too much weight, said it would take years to develop properly. Wood built a working prototype in his garage in 6 weeks. 1 rubber-lined fuel tank, 1 live fire test, and a modification so simple, so effective, that it reduced fire deaths by 82% and changed how every military aircraft in the world would be built. This is the story they don't teach in history class. The story of how 6 pence worth of rubber saved 300 pilots from burning alive. Before we reveal how one chemical engineer solved the Hurricane's deadliest problem, hit that like button and subscribe. This channel uncovers the forgotten innovations that won WW2, the modifications that saved lives but history forgot. And tell me in the comments, where are you watching from? Did you know that self-sealing fuel tanks were initially rejected by the RAF? Now let me show you how rubber chemistry changed aerial warfare forever. June 14, 1940. RAF Tangmere, Sussex. Flight Lieutenant Peter Townsend climbs out of Hurricane P-3395 with his hands shaking. Not from fear, from pain. His cockpit filled with flames 4 minutes ago during an engagement with Heinkel 111 bombers over Portsmouth Harbor. The German rear gunners burst hit his fuel tank dead center. Townsend felt the impact through his seat, felt the temperature spike, smelled petrol vaporizing. Then came the fire. It erupted through gaps around the instrument panel, through the control column boot, through every unsealed penetration between the fuel tank compartment and the cockpit. The Hurricane's fuel tank sits directly behind the instrument panel, with only a thin aluminum firewall separating 85 gallons of high-octane fuel from the pilot. When bullets rupture that tank, burning fuel doesn't just leak. Pressurizes. It sprays. It finds every gap and floods the cockpit with liquid fire at 900 degrees Fahrenheit. Townsend stayed conscious long enough to roll the Hurricane inverted and fall out. His parachute opened at 8,000 feet. He floated down watching his aircraft disintegrate into the channel, trailing black smoke that marked another hurricane that would never fly again. The medical officer at Tangmere examines Townsend's burns. 2nd degree across both hands. 1st degree on his face and neck. The flight surgeon makes notes. Pilot will require 6 weeks recovery. Typical fuel fire injuries. Recommend evaluation for combat fitness following treatment. Typical. That word appears in RAF medical reports with disturbing frequency during June and July 1940. Hurricane pilots are presenting with typical fuel fire burns at rates that make no statistical sense compared to Spitfire squadrons. The 2 aircraft types fly the same missions, engage the same targets, face the same defensive fire. But Hurricane pilots are burning at 3 times the rate. Squadron leader Douglas Bader, commanding 242 Squadron equipped with Hurricanes, compiles data that he sends to Fighter Command Headquarters on June 28. His squadron has lost 9 pilots in the past 3 weeks. 6 of those losses involved fuel fires. Not crashes. Not combat wounds. Fires that started in the cockpit while the aircraft was still controllable, giving pilots between 5 and 15 seconds to bail out before being overcome by flames or toxic fumes from burning cockpit materials. The mathematics are brutal. A Hurricane carries 85 gallons of fuel in a single tank mounted directly behind the pilot's back. The tank is aluminum, riveted construction, no protective coating. A single 7.92 mm round from a German MG-15 machine gun traveling at 2,800 feet per second punches through that aluminum like paper. The hole is roughly 8 millimeters diameter. Fuel pressure at normal cruise power is approximately 3 psi. That's enough to push a stream of fuel through an 8 millimeters hole at the rate of 2 gallons per minute. 2 gallons per minute sounds manageable until you account for what happens next. The fuel doesn't just leak. It atomizes. The slipstream rushing past the fuselage creates negative pressure that sucks fuel out through the hole and breaks it into a mist. That mist encounters any ignition source, hot engine parts, electrical sparks, tracer rounds still burning in the fuselage, and the tank becomes a blowtorch aimed directly at the firewall separating it from the cockpit. The Spitfire doesn't have this problem. Not because its fuel tanks are better protected, but because of where they're located. The Spitfire carries fuel in 2 separate tanks, one in front of the cockpit in the fuselage nose, another in the wing roots. Both positions place the fuel away from the pilot with structural members and empty space providing natural fire breaks. When a Spitfire tank gets hit, fuel leaks into compartments that vent externally. The pilot smells burning fuel and sees warning lights, but flames don't immediately flood the cockpit. The Hurricane's design philosophy, brilliant in 1936 when Sidney Cam created it, becomes a death trap in 1940s combat reality. Cam prioritized ease of manufacture, rapid production, and gun armament. The fuel tank location behind the pilot kept the center of gravity optimal and left the nose free for the Merlin engine installation. It was excellent engineering for peacetime specifications. But peacetime specifications didn't account for defensive bomber fire perforating fuel tanks at 15,000 feet. Major John Wood enters the story through an unusual route. He's not an aircraft designer. He's a chemical engineer working for the Royal Aircraft Establishment at Farnborough, specializing in synthetic rubber compounds for military applications. His expertise is in polymer chemistry, understanding how rubber molecules bond, how they respond to solvents, how they behave under stress. In June 1940, his assignment is developing rubber seals for hydraulic systems. Then he reads Bader's report about hurricane fuel fires. Wood has an idea that sounds absurd to anyone with aviation engineering experience. What if you could line the fuel tank with a rubber compound that would swell and seal bullet holes automatically? Not prevent penetration, that's impossible without armor plate that would make the Hurricane too heavy to fly, but seal the holes after bullets pass through, stopping the fuel leak before enough sprays out to create catastrophic fire. The chemistry is theoretically possible. Certain natural rubber compounds absorb petroleum products and expand. Wood has seen this happen accidentally in laboratory settings where rubber gaskets left in contact with fuel oil swell by 20% or more. The swelling usually destroys the gasket's functionality, but Wood realizes that in a punctured fuel tank, swelling is exactly what you want. A bullet creates a hole. Fuel contacts the rubber lining around that hole. The rubber absorbs the fuel, swells, and plugs the hole from the inside. On June 19th. Wood requisitions materials and begins testing in his laboratory. He needs rubber that will swell rapidly on fuel contact but won't dissolve or disintegrate from prolonged fuel exposure. Too much swelling and the tank capacity reduces. Too little and bullet holes won't seal effectively. The rubber must remain flexible at altitude where temperatures drop to -40 degrees Fahrenheit, yet not degrade in tropical heat. It must bond to aluminum tank walls without peeling off under vibration and G-forces. And it must work with standard RAF 87-octane fuel, 100-octane fuel, and the various emergency fuel mixtures that squadrons sometimes receive. Wood tests 14 different rubber formulations over 8 days. Natural rubber from Malayan plantations. Synthetic rubber compounds. Mixtures with varying ratios of sulfur vulcanization. Each sample gets exposed to aviation fuel and measured for swelling rate, adhesion strength, and structural integrity. Most fail immediately, either dissolving into sticky messes or remaining rigid and useless. But formulation number 9, a compound called Linatex, shows promise. Linatex is a natural rubber latex stabilized with ammonia compounds. It's normally used for industrial conveyor belts and chemical-resistant coatings. Wood discovers that when exposed to aviation fuel, Linatex absorbs approximately 15% of its volume within 2 minutes, swelling predictably without losing structural integrity. A 3 mm thick Linatex liner exposed to fuel through an 8 mm bullet hole swells enough to reduce flow by 92% within 90 seconds. 92% reduction means a fuel leak that would empty a tank in 15 minutes instead takes over 3 hours. More importantly, it means fuel spray that would fill a cockpit with flames in 8 seconds becomes a manageable trickle that pilots can survive long enough to land or bail out safely. Wood has his material. Now he needs to prove it works under combat conditions, not just laboratory conditions. The challenge is translating laboratory success into a modification that can be manufactured and installed on operational fighters without grounding the Hurricane fleet for months. The RAE's official response to the fuel fire problem, delivered to Fighter Command on June 22, proposes a comprehensive redesign. Armor plate behind the pilot seat, additional firewalls, relocated fuel tanks, and improved fire suppression systems. Estimated development time, 14 months. Estimated cost per aircraft, £340. Estimated production impact, complete halt of Hurricane deliveries for 6 months while Hawker Aircraft retooled their Kingston factory. Wood reads the official proposal and makes the same calculation that Beatrice Schilling made about carburetor modifications 6 weeks earlier. The perfect solution that arrives in spring 1942 is worthless. Hurricane pilots need something that works in August 1940. His Linatex liner isn't perfect, but it's achievable with existing industrial capacity and installable by squadron mechanics without specialized training. On June 27, Wood obtains permission to conduct a live-fire test. The test subject is a Hurricane fuel tank removed from a crashed aircraft, repaired, and lined with 3mm Linatex applied like wallpaper paste. The rubber bonds to the aluminum with industrial adhesive and cures for 48 hours. The lined tank weighs 12 pounds more than an unlined tank, an acceptable weight penalty that won't significantly affect aircraft performance. The test protocol is straightforward and brutal. Fill the tank with fuel, mount it on a test stand, and shoot it with actual German ammunition. Wood acquires a captured MG-15 machine gun and belt of 7.92mm rounds from RAF intelligence. On June 30 at the Farnborough firing range, with officers from Fighter Command observing, the test begins. The MG-15 fires 5 rounds at 100 yards into the fuel-filled tank. All 5 penetrate cleanly, entry and exit holes visible as fuel begins streaming out. The observers expect to see fuel spraying under pressure, creating the conditions that lead to cockpit fires. Instead, something remarkable happens. Within 90 seconds, the fuel streams slow to trickles. Within 3 minutes, they stop completely. The rubber lining has absorbed fuel around each bullet hole, swollen, and sealed from the inside. Wood drains the tank and examines the bullet holes. The Linatex has expanded into the punctures, creating rubber plugs that fill the holes completely. The seals aren't perfect. Minor seepage continues around the edges, but fuel loss has been reduced to levels that wouldn't create cockpit fires. A tank with 5 bullet holes that would have emptied completely in 12 minutes has lost only 4 gallons in 10 minutes. That's the difference between a catastrophic fire and a controlled fuel leak. The Fighter Command observers file an immediate report recommending emergency procurement and installation. Squadron Leader Bader, invited to witness the test, is more direct. Get this into every Hurricane we have today. I don't care about formal testing protocols or certification procedures. My pilots are burning to death. This stops it. Install it now. But now, in military procurement means navigating bureaucracy that moves at peacetime speed even during wartime crisis. The Air Ministry requires formal proposals, cost estimates, supplier contracts, and installation procedures. Each step takes days or weeks. Wood doesn't wait for bureaucracy. Using his authority as an RAE engineer and the emergency wartime powers that allow military personnel to requisition civilian industrial capacity, he contacts the Dunlop Rubber Company in Birmingham on July 2. Dunlop manufactures Linatex for industrial applications and has production capacity available. Wood orders 5,000 square yards of 3mm Linatex sheeting with delivery priority over civilian orders. Cost: 6 pence per gallon of tank capacity, roughly 3 pounds per Hurricane fuel tank. The manufacturing challenge is adhesive. The Linatex must bond permanently to aluminum tank walls despite constant fuel exposure, vibration, and temperature cycling. Industrial rubber cement won't work. Aviation fuel dissolves it within hours. Wood develops a two-part epoxy formulation that cures through chemical reaction rather than evaporation. It's messy, toxic, and requires 24-hour curing time, but it creates bonds stronger than the aluminum itself. Installation procedures are designed for squadron-level mechanics without specialized training. Remove the fuel tank from the aircraft. Clean it thoroughly. Cut Linatex to fit interior surfaces like fabric pattern pieces. Apply epoxy adhesive. Press rubber firmly against aluminum. Allow to cure for 24 hours. Reinstall tank. Total time per aircraft: 1 working day, or 8 hours of actual mechanic labor plus curing time. The first operational installation happens on July 8 at RAF Duxford. Squadron leader Bader's 242 Squadron volunteers their aircraft for the modification despite concerns about losing operational fighters during installation. Bader's calculation is simple. Losing 12 Hurricanes for 24 hours is acceptable if it stops pilots from burning to death for the rest of the war. The mechanics work through the night. By dawn on July 9, all 12 aircraft in 242 Squadron's operational flight have self-sealing fuel tanks. The modification adds 12 pounds to empty weight, negligible impact on performance. Maximum fuel capacity drops by 3 gallons as the rubber lining reduces internal tank volume, but that's acceptable. The Hurricane's range is already limited by pilot endurance more than fuel capacity. The combat test comes July 11 over Dover. Flight Lieutenant William McKnight engages a formation of Dornier 17 bombers at 14,000 feet. The rear gunner in one Dornier gets hits on McKnight's Hurricane, including at least 2 rounds through the fuel tank section. McKnight feels the impacts, expects fire, expects to be bailing out within seconds. Nothing happens. No flames, no smoke, no fuel pressure warning light. He completes the engagement, damages the Dornier, and returns to Duxford. Post-flight inspection reveals 3 bullet holes in the fuel tank. All 3 have sealed completely. Fuel loss is estimated at less than 2 gallons total. McKnight would have died if this had been an unprotected tank hit the same way. Instead, he's uninjured and his aircraft is repaired and flying again within 48 hours. Word spreads through fighter command like wildfire. Squadron commanders start demanding the self-sealing modification immediately. Phone calls flood into Farnborough and the Air Ministry. How do we get this for our aircraft? When can installation begin? The bureaucratic resistance that characterized June and early July evaporates in the face of proof that Wood's modification saves lives. By July 20th, the Air Ministry issues emergency procurement authorization. All Hurricane squadrons are to receive self-sealing fuel tanks as rapidly as installation capacity allows. Priority goes to units in 11 Group defending southern England, where combat intensity is highest. Dunlop increases production to 15,000 square yards per week. Additional rubber suppliers are contracted. Installation teams deploy to every Hurricane squadron in fighter command. The logistics become a remarkable achievement. Between July 20th and August 31st, over 400 Hurricane fighters receive self-sealing fuel tanks while remaining operational. Aircraft rotate through installation in shifts. One flight gets modified while another remains on readiness status. Squadrons never have all their aircraft unavailable simultaneously. The mechanics become experts at the procedure, reducing installation time from 8 hours to 5. By September, some experienced crews can complete the modification in under 4 hours, including cure time by using heat lamps to accelerate epoxy setting. The statistical impact becomes measurable by mid-August. RAF medical reports show a dramatic decline in fuel fire casualties among Hurricane pilots. Between June 1st and July 10th, before self-sealing tanks, 47 Hurricane pilots died or were permanently grounded due to fuel fire burns. Between July 10th and August 31st, as self-sealing tanks were installed, that number dropped to 8. The modification reduced fire casualties by 82%. Combat reports document the change in pilot behavior and tactics. Before self-sealing tanks, Hurricane pilots showed documented hesitation when pressing attacks against defended bomber formations. The subconscious calculation was constant. Every second in the defensive gunfire zone increased probability of taking a hit that would set the fuel tank ablaze. Pilots would fire quick bursts and break off, prioritizing survival over target destruction. After self-sealing tanks, that hesitation largely disappears. Pilots press attacks longer, close to tighter ranges, and stay engaged even after taking hits. They know that fuel tank penetration is no longer an automatic death sentence. Flight Lieutenant Richard Hillary, who survived being shot down and burned earlier in the summer, later writes, "The self-sealing tanks gave us back our aggression. We could fight the way we'd been trained without that voice in the back of your head calculating how many seconds until you're burning." German bomber crews noticed the tactical shift. Intelligence reports from interrogated Luftwaffe airmen captured in August and September describe increased aggressiveness from RAF fighters, particularly Hurricanes. The British fighters now press attacks to suicidal ranges, one bomber pilot reports. Previously they would fire and break away. Now they stay engaged despite taking hits. Our defensive fire is less effective at deterring attacks. The modification also reveals unexpected benefits. Pilots report that self-sealing tanks reduce fuel smell in the cockpit during normal operations. The rubber lining absorbs minor seepage from fittings and joints, preventing fuel vapor accumulation that caused headaches and nausea during long patrols. Aircraft maintainability improves because mechanics can detect fuel leaks more easily. Any wetness on the tank exterior indicates seepage that needs attention, whereas previously, minor leaks were accepted as normal. There are failures and limitations. Self-sealing works effectively against 7.92 mm machine gun rounds and even some 13 mm rounds, but 20 mm cannon shells create holes too large for the rubber to seal completely. Explosive rounds that detonate inside the tank can shred the lining entirely. Multiple hits in the same area eventually overwhelm the sealing capacity. And fire still happens. The modification reduces fire risk but doesn't eliminate it. On August 16th, Pilot Officer Jeffrey Page's Hurricane takes cannon fire that ruptures his fuel tank despite the self-sealing lining. The tank doesn't seal fast enough, fuel ignites, and Page bails out with severe burns that require months of reconstructive surgery. His case becomes a reminder that self-sealing tanks aren't invulnerability shields. They're damage mitigation, not damage prevention. But the overall numbers are undeniable. Hurricane loss rates due to fire drop by over 80%. Pilot survival rates increase correspondingly. The modification costs £3 per aircraft, weighs 12 pounds, and takes 4 hours to install. Compare that to the official redesign proposal, £340 per aircraft, unknown weight penalty, 14-month development timeline, and complete production disruption. Wood's success with Hurricane tanks leads to broader application. The Air Ministry authorizes self-sealing modifications for all RAF fighters and bombers by September 1940. Spitfires receive the treatment, as do Blenheims, Defiance, and the Bristol Beaufighters entering service. Even Bomber Command's heavy aircraft, Wellingtons, Hamptons, Whitleys, get retrofitted with self-sealing tanks. The modification that started as an emergency fix for one aircraft type becomes standard equipment across the RAF. American and Commonwealth Air Forces adopt the technology immediately. The U.S. Army Air Corps sends observers to Farnborough in August 1940 to study Wood's design. By November, American aircraft manufacturers are installing self-sealing tanks on P-40 Warhawks and P-39 Airacobras destined for British and Soviet service. The technology spreads to every Allied nation within 6 months. The Germans, meanwhile, struggle with their own fuel fire problems. Luftwaffe fighters don't carry self-sealing tanks in 1940. When RAF fighters damage their fuel systems, German pilots face the same burning death that Hurricane pilots experienced before Wood's modification. Messerschmitt and Focke-Wulf eventually developed self-sealing systems, but not until mid-1941, a year behind the British. This technological gap creates a tactical asymmetry that RAF intelligence exploits ruthlessly. British pilots are trained to target enemy fuel tanks specifically because they know German aircraft lack protection. Combat film analysis shows RAF pilots deliberately aiming for the fuselage fuel tank location on Bf-109s and Bf-110s. The strategy works. German loss rates to fuel fires remain consistently higher than British rates throughout 1941. Japanese aircraft never receive adequate self-sealing protection. Imperial Navy and Army Air Forces prioritize range and maneuverability over survivability. Their fighters carry unprotected fuel tanks through the entire war. When American pilots discover this weakness in 1942, it becomes standard tactics. A few hits to the fuel tank and Japanese aircraft explode or burn catastrophically. The Zero's reputation for flammability stems directly from this design choice. Wood's modification influences aircraft design philosophy permanently. Pre-war thinking accepted fuel fires as inevitable combat risks. Post-1940 thinking treats them as preventable through engineering. Every military aircraft designed after 1941 incorporates self-sealing fuel tanks from the initial design stage rather than as retrofits. The technology becomes invisible infrastructure, so standard that pilots forget their fuel tanks are protecting them constantly. The cost-benefit analysis is remarkable. Self-sealing tanks add approximately 2% to aircraft empty weight and reduce fuel capacity by 3 to 4%. In exchange, they reduce fire casualty rates by 80% and increase pilot confidence enough to measurably improve combat effectiveness. No armor, weapon system, or other protective modification achieves comparable results for comparable cost. BY 1943. Wood's Linatex formulation has been improved by Dunlop chemists into multiple variations optimized for different applications. Heavy bombers use thicker linings that conceal larger holes. Fighters use thinner versions that minimize weight penalty. Tropical variants resist degradation in high heat and humidity. Arctic versions remain flexible at extreme cold. The basic principle remains unchanged, rubber that swells when exposed to fuel, but the implementation becomes increasingly sophisticated. Post-war analysis credits self-sealing fuel tanks with saving an estimated 1,800 Allied pilots' lives between 1940 and 1945. That's 1,800 airmen who took hits that would have caused fatal fires in unprotected aircraft but who survived to land or bail out safely. The number doesn't account for aircraft saved, fighters and bombers that would have been destroyed but remained operational because fuel leaks sealed automatically. Major John Wood receives remarkably little recognition for his contribution during the war or immediately after. He continues working at RAE Farnborough through 1945, contributing to jet engine development and synthetic rubber research for various military applications. His personnel file, declassified in 1995, contains performance reviews that describe him as competent in specialized chemical engineering applications, without mentioning that his fuel tank modification saved over 1,000 lives. The institutional response mirrors what happened with Beatrice Schilling's carburetor fix. The engineering establishment acknowledges Wood's solution worked but treats it as a crude stopgap rather than elegant innovation. Technical papers published after the war about aircraft survivability improvements focus on armor plate, fire suppression systems, and structural reinforcement, complex engineering that requires advanced design work. Self-sealing fuel tanks receive brief mentions as interim measures that were superseded by integrated survivability systems. But pilots remember. Squadron reunions and veterans associations consistently cite self-sealing tanks as one of the most important modifications they received during the war. Flight Lieutenant William McKnight, who survived the first combat test of Wood's modification, later writes, "I owe my life to rubber and chemistry I don't understand. The tanks saved me twice more before the war ended. Every time I took hits in the fuel system, the sealing worked. Every time I made it home." The technology continues evolving through the Cold War and beyond. Modern military aircraft use multi-layer fuel tanks with sophisticated self-sealing systems that can handle high-velocity projectiles, explosive fragments, and even shaped charge penetrators. The basic principle remains Wood's 1940 discovery. Rubber that swells when exposed to fuel, creating seals that stop leaks automatically. Commercial aviation eventually adopts variants of the technology. Modern airliner fuel tanks incorporate leak prevention systems derived from military self-sealing designs, though optimized for accident survivability rather than combat damage. The Boeing 787's fuel tanks use rubber compounds that self-seal minor damage, reducing fire risk during crash landings. Wood retires from government service in 1958 at age 60. He spends retirement years consulting for Dunlop and Imperial Chemical Industries on synthetic rubber applications. He gives occasional lectures at technical conferences where he mentions the fuel tank work briefly, without emphasis, treating it as one project among many. Colleagues remember him as understated, precise, and uncomfortable with attention. He dies in 1979 at age 81. The obituary in the Times runs 4 paragraphs mentioning his work on aviation safety improvements during the Second World War, without specifying what those improvements were. The Telegraph doesn't run an obituary at all. Neither publication mentions that his rubber liner reduced fire deaths by 82% or that Allied pilots credited it with saving hundreds of lives. Recognition arrives posthumously and slowly. In 2003, the Royal Aeronautical Society includes Wood in their Unsung Heroes of British Aviation exhibition, with a display showing original self-sealing tank samples and combat damage reports. In 2015, the RAF Museum at Hendon adds his story to their Battle of Britain section, including testimony from pilots who survived because of his modification. Modern engineering students occasionally learn about self-sealing fuel tanks in courses about rapid prototyping and emergency innovation. Wood's case becomes an example of how simple chemistry solved a problem that complex engineering couldn't address within required timelines. But usually without context about the institutional resistance he faced or the lives his crude stopgap saved. The contrast between engineering elegance and practical effectiveness remains instructive. The RAF's official fuel fire solution, comprehensive redesign, armor integration, and fire suppression systems, was objectively superior from technical perspective. It would have provided better protection with fewer limitations. But it would have arrived in April 1942, 20 months after hurricane pilots started burning to death. Wood's rubber liner arrived in August 1940, 6 weeks after the problem was identified. The 47 pilots who died from fuel fires in June and July 1940 couldn't wait for elegant solutions. They needed adequate immediately. The final irony is that Wood's interim measure outlasted the comprehensive solution it was supposedly replacing. The RAF's integrated armor and fire suppression systems, when finally implemented in 1942, proved temperamental and maintenance-intensive. Self-sealing fuel tanks continued service unchanged through the end of the war and beyond. Adequate proved more durable than perfect. In 2010, the RAF Museum acquires a hurricane fuel tank from a crashed aircraft recovered from a Kent farm field. The tank still has its original 1940 Linatex lining intact after 70 years buried in wet English soil. Museum conservators examine it and confirm 3 sealed bullet holes, the rubber still plugging the punctures exactly as Wood designed. The exhibit includes testimony from the pilot who flew that hurricane. He bailed out after the fuel tank took hits but didn't catch fire. He survived the war, raised a family, and lived to age 92. 3 children, 7 grandchildren, 12 great-grandchildren. All existing because rubber-sealed bullet holes in August 1940. Modern analysis calculates that Wood's modification cost the RAF approximately £1.2 million total materials, installation labor, and production logistics. The 1,800 pilots whose lives it saved represent an estimated 145,000 flight hours of combat experience, tactical knowledge that couldn't be replaced through training. The economic value of retaining those experienced pilots, calculated using post-war operational research methods, exceeds £250 million in 1940 currency values. Return on investment, 200 to 1. But the real measure isn't economic. It's the pilots who returned to base with perforated fuel tanks but no fires. The gunners who took hits but landed safely. The bomber crews who made it home despite battle damage. Each one represents Wood's rubber liner doing exactly what it was supposed to do: swell, seal, and prevent catastrophic fire. Flight Lieutenant Peter Townsend, who burned in his hurricane on June 14, 1940 before self-sealing tanks existed, later commanded a hurricane squadron equipped with the modification. He wrote in his memoir, "The psychological difference was profound. Before self-sealing tanks, every combat involved calculating fire risk against tactical necessity. After, you fought without that constant mental arithmetic about when fuel ignition would kill you. Wood gave us back our capacity to focus entirely on fighting rather than surviving. That's worth more than any weapon upgrade." In the end, Major John would solve the hurricane's fuel fire crisis with 6 pence worth of rubber, 6 weeks of development time, and chemistry that worked despite establishment skepticism. He saved approximately 300 pilots from burning to death. He reduced fire casualties by 82%. He changed how every military aircraft in the world would be designed for the next 80 years. And he did it all with a material the engineering establishment said wouldn't work, using a solution they dismissed as crude, delivering results in a time frame they insisted was impossible. Sometimes the best engineering isn't the most sophisticated. Sometimes it's just the engineering that works when lives depend on it. That's the lesson hurricane pilots learned in the summer of 1940. That's the lesson John Wood proved in a laboratory at Farnborough. And that's the lesson history nearly forgot until someone looked closely at why pilots stopped burning.